Next up, we are going to look at the concept that relates mass and volume. And as was already suggested when we talked about the lead and the feathers, they differ in terms of their density. And we define the density like this. We define the density as being the mass per unit of volume. The mass per unit of volume. Now the wording is important here because if we look at the word per in mathematics, what does the word per mean that we do? It means we divide. It means we divide. So this tells us that we're going to take mass and divide by volume. And so if we wrote a formula for that, we'd say that the density is equal to mass over volume. And in terms of symbols, we'd say that D is equal to M over V. And so in terms of formulas to know, use, memorize, whatever, we don't have many mathematical formulas we memorize in here, but this is one we will use, and that is D is equal to M over V. So now, when we want to measure the density of something, let's say that we have this block of wood, and I had to run and get this morning. This has been with me about 30 years, and I cracked it, so I had to glue it together. But what we'd like to do is we'd like to measure the density of this block of wood. So in order to measure its density, which measurements are we going to need? Mass and volume. How do we measure mass? How do you measure mass? You just done it in the lab. The scale, sure. One of these scales would work. How are we going to measure the volume?
Measure it.
You know, how do we measure it?
Like a ruler?
Ruler would work. And what are we going to need to do with a ruler? Length times width times height. And we'll ignore the little chip off the corner, all right? So length times width times height is what we need. So we're going to go ahead and measure the density of this block of wood. And our formula, again, that we'll be working with is D is equal to M over V. And very conveniently, I happen to have brought a scale here into lab today. So we will, here we go, put this on the scale and measure its mass. We will zero it and put this on. We can go ahead and record this as 232.67. And of course the units on that would be grams. Then the next thing we're going to do is measure the volume, and as was suggested, we need the length, width, and height. Now I did not bring my glasses in here today, so rather than estimating to the nearest hundredth, we will estimate to the nearest tenth, coming up with 16.8, and of course that would be in units of, what do you think?
Centimeters.
Centimeters. And then another dimension that we have here would be 8.7 centimeters. And then the thickness of this thing, 3.7 centimeters. Now again, I'm writing them all out like this because one of the things we'd like to do when we perform calculations is we'd like to eliminate as much potential calculation error as possible so we can set it all up into a single calculation. And so if you run this through your calculators, and here's how I would suggest doing it. Remember that we multiply everything together that appears in the numerator and divide by each value that appears in the denominator. Maybe I'll start typing 232.67. We divide that by 16.8. We divide it again by 8.7. We divide it again by 3.7. And upon doing so, it looks like we wind up with 0.4302, etc. Now, how many significant figures should be in that answer?
2.
2. So rounding it off to two significant figures, we get 0.43.
4.3
The units would be
grams per centimeters cubed.
grams per centimeters cubed, exactly. I would actually say grams per cubic centimeter. And so, taking out the two significant figures, because the least of all of these here will be these two, which have two significant figures, meaning our answer should have two significant figures as well. Now, when we get an answer like this, we should ask ourselves, does this answer make sense? We should actually have a basis for answering that. And how do we know whether it does or doesn't? Well, what happens if I go out to the Mississippi River and just throw this out there? What's going to happen to it? Going to sink or is it going to float? It should float. Does this represent an answer of something that would float? And how would we even know? Well, what would we have to compare it to? Density of water. Anybody know what the density of water is? It's a very convenient number. 1, exactly. In units of grams per cubic centimeter, the density of water is 1 gram per cubic centimeter. You should always then, when you calculate a density, ask yourself if it makes sense by comparing it to the density of water, which again has a value of 1 gram per cubic centimeter. And so, does this answer make sense?
Yeah.
Yes, because its density is less than that of water. If the density was greater than that of water, then the object would sink in water. So again, we always make that comparison. Now the other thing about water is we say that it is about 1 gram per cubic centimeter because density is something that changes with temperature. When things warm up, they tend to expand. When they cool down, they tend to contract. Okay? A hot air balloon is a very good example of that. If you want to float, anybody ever been in a hot air balloon? Okay? Well, if you want the hot air balloon to go up, what do? You heat up the air. You simply got a big flame, you put underneath that balloon, you start heating it up. Once you heat it up then, that air in there begins to expand. And as it expands, that air inside of that balloon gets to be lighter than the air surrounds it. As a result then, the hot air balloon lifts up, rises up off the ground. So the same is true with water. When we talk about water having a density of 1 gram per cubic centimeter, that's at a temperature of 4 degrees Celsius. That's not that you really need to know that exact fact. It's actually like 3.97 some degrees Celsius. But that's where water has its maximum density. And if you increase the temperature above 4 degrees Celsius, then the density will go down. Now the other thing is that when we look at a value like this, we need to remember that 1 cubic centimeter is the same as 1 milliliter, which of course again is the same as 1 cc. Which means that another way that we could write this density is as 0.43 grams per milliliter, or grams per cc. Typically, however, we see the units expressed for density one of these two ways. But does it really matter? No, because cubic centimeter and a milliliter are the same thing. So the units of milliliters and cubic centimeters are interchangeable. That's the first calculation. Any questions on this one here? Right, in our next demo, we have an empty graduated cylinder. Has a mass of, right now we'll just say blank. And then we're going to say blank milliliters of water at 24 degrees Celsius was added to the cylinder. And then the question is, what is the combined mass of the cylinder and water? When we look at this here, with the temperature 24 degrees Celsius, one of the things we need to know is that the density of water at 24 degrees Celsius is equal to 0.997 grams per milliliter. So we'll start with the graduated cylinder. We'll go ahead and make some measurements. We're going to fill in the first blank here. And we'll put the cylinder on the balance. 0 at first. Looks like the empty cylinder is 100.46. Or actually 0.45. And of course the fact we saw 4-6 and now 4-5 and back to 4-6, what does that illustrate about the last digit?
Uncertain.
Uncertain, exactly. So I'm writing down 100.46. Then we're going to go ahead and put some water in here. We're going to let those air bubbles escape from the water. If we think about what it is we're looking for, what are we trying to find in this particular problem?
Combined mass.
Combined mass. So let's think about what we do know about the mass. Which mass do we know? Right, so let's just jot down some information we do know. We do know the mass of the cylinder, and that mass of the cylinder is 100.46 grams. And if we want to find the combined mass of the cylinder and water, then which mass do we need to calculate? Water. We need to find the mass of the water. Now, do we know what the mass of the water is? I know I could put that on the balance, but I'm not going to do that. Do we know what the mass of the water is? No, we don't. Okay, now we do know the volume, and I'm waiting for those air bubbles to come out, so we'll come back to that. So the combined mass would simply be, how do we find the combined mass with these two? Add them together. And of course, then that's going to give us the combined mass of the cylinder and water. Now, what we also know here is the formula for density. We know that the formula for density, D, is equal to m over v. And if we look at the information we do have, and we might as well go ahead and measure this right now, just short of 54, so I guess about 53.9 milliliters is how much we have. So we'll fill in this blank. We have 53.9 milliliters of water at 24 degrees Celsius was added to the cylinder. So if we look at this formula right here, D is equal to m over v. Do we know the density?
Yep.
0.997. Do we know the mass?
No.
No, we don't. Do we know the volume?
Yes.
Yes, and what is the volume? 53.9 milliliters. So if we know the volume and the density, we should be able to use that to find the mass. So now, this is where you need to have that little bit of algebra and why it's a prereq for coming in here. If we want to find the mass, what do we need to do to each side?
Times the volume.
Times the volume. So multiply each side by v. When we do that, v cancels out, and that tells us that m, the mass, is equal to v times d. The volume, once again, 53.9. I just don't always listen to myself. Okay, so we'll take 53.9, multiply it by 0.997, and we get 53.7383, which of course, though, if we look at significant figures, that means we would round this off to 53.7. So we come up here then, we put in the 53.7, which is the mass of the water. We then sum this together. We take 100.46, add to it 53.7, and we get an answer of 154.16, which of course we should actually round off to 154.2. The label on this would be grams. Okay, remember now that the reason why we do this is because the 7 here is the uncertain digit. When we add and subtract, we don't look at significant figures, we look at decimal places. So we should have 154.2 grams. So if we come back here then, and we place this onto the balance, we want to check to see how we did with that. It looks like we wind up with 154.57 grams. So the value we're showing here is 154.57. We said, though, it would be 154.2. Is that an acceptable answer? So again, we measured 154.57 grams. Is that what we should expect? Because remember, this digit here would be considered the uncertain digit. So we would expect to see some variation in this digit right here, and we did. So any questions on the calculations? Okay, now let's suppose that we had wanted to calculate the volume. We had a calculation where we had to find the volume. So if we have D is equal to M over V, and we want to find V, this is something that often gives students problems. When we have to solve for M is great, we're given V, but when we have something in the denominator, this is where I see lots of errors. And that's because we can't solve for it while it's still down here in the denominator. We have to move it into the numerator. We have to move it somewhere up there. So we have to get it up on the same line. So the way we do that is to take each side and multiply by V. When you multiply each side by V, it cancels out. Then to get V by itself, divide by D. And again, if we do something to one side, we have to do it to the other side as well. So we divide the left-hand side by D, we divide the right-hand side by D, and when we come up with it, we find out that V is equal to M over D. So again, V is equal to M over D. So that's the algebra. Now if you're algebra challenged, I have something called the density pie. And the density pie looks something like this. And what we're going to do here is we're going to put M up on top. This is what we call a mnemonic. Anybody know what a mnemonic is? Mnemonic is simply a
Phrase.
well, it could be a phrase.
Just a device to remember.
Device to remember. Sometimes corny. And you're going to learn lots of corny memory aids in here. But here's one that I like to call the density pie. And if you want to remember how to get started on this one, give me the biggest slice. I'm going to put that one on top. Give me the biggest slice and put me on top. Okay, for M. Then we're going to put VD on the bottom. Now, if you want to calculate any one of these, here's how the density pie works. If you want to find D, we cover it up. And it says we take M over V. If you want to calculate D, we cover it up. And it says we take M over D. If we want to calculate M, we cover it up. And we take D times D. This is the density pie. The density pie will always work when you work with the calculations here. So, any questions with that? And just remember to give yourself the biggest slice and put yourself on top. And we're good.